Welcome to my online course in linear algebra for undergraduate mathematics. Today's topic of discussion is dimension of a vector space. The number of elements in a basis of a vector space is called dimension of a vector space. It is denoted by time V. If the dimension of V is finite, then V is said to be finite dimensional vector space. Otherwise, the vector space is said to be infinite dimensional. Next is theorem on dimension of a vector space. First theorem, if V is a finite dimensional vector space of dimension n, then any set of n plus 1 vectors of V is linearly dependent. Proof. Given V is finite dimensional vector space of dimension n, so every basis of V will contain exactly n element. Let S be a subset of V containing n plus 1 vectors. If S is linearly independent, then either S itself is a basis or it can be extended to form a basis of V by using extension theorem. In any case, we are getting a basis of P containing more than an element, which is a contradiction, and this contradiction arises because we have considered S to be linearly independent subset of P. Therefore, S must be linearly dependent. Next theorem, if V is a vector space of dimension n, then any linearly independent subset containing exactly n element is a basis of V. Proof, since V is a vector space of dimension n, so every basis of V will contain exactly n elements. Since S is linearly independent subset containing n element, so if S is not a basis of V, then it can be extended to form a basis of V by using extension theorem. So V will have a basis containing more than n element, which is a contradiction. Therefore, S must be a basis of V. Next, if this is a vector space of dimension n, then any set containing n element such that linear span of S is equal to V will be a basis of V. Since V is a vector space of dimension n, so any basis of V will contain exactly n element. If S is not a basis of V, then we will get a basis of V which will be a proper subset of S containing less than n element, which is a contradiction. As V is a vector space of dimension n, so any basis of V will contain exactly an element, not less than an element. Therefore, S must be a basis of V. Next theorem, if V is a basis of finite dimensional vector space, then every element of V can be uniquely expressed as the linear combinations of the element of V. Let V equal to V1, V2, Vn be a basis of V. If possible, let V belongs to V. Vector space V can be expressed in two different forms as V equal to alpha 1 V1 plus alpha n Vn. V equal to beta 1 V1 plus beta n Vn. Then equating the right hand side of both the expression for V, we will get alpha 1 V1 plus alpha n Vn is equal to beta 1 V1 plus beta n Vn. Next step, we take this element to left hand side, then rearrange the term. We will get alpha 1 minus beta 1 V1 plus alpha 2 minus beta 2 V2 plus alpha n minus beta n Vn is equal to 0. Since P is linearly independent, therefore these scalars are all 0. That is alpha 1 minus beta 1 is equal to 0, alpha 2 minus beta 2 is equal to 0, alpha n minus beta n is equal to 0. This implies alpha 1 is equal to beta 1, alpha 2 equal to beta 2, alpha n equal to beta n. That means if there are two different linear combinations of the vector V, then the set of scalars are equal. That means every element of V can be uniquely expressed as the linear combinations of the element of V. Therefore, hence the theorem. Next, if W1 and W2 are subspace of a finite dimensional vector space V, then dime of W1 plus W2 equal to dime of W1 plus dime of W2 minus dime of W1 intersection W2. Since W1 and W2 are subspace of a finite dimensional vector space, so there are some W1 plus W2 and their intersection W1 intersection W2 are all subspace and they are finite dimensional. Let dimension of W1 intersection W2 be K and B1 equal to the set U1 U2 dot 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 UK be the basis of W1 intersection W2. Since W1 intersection W2 containing both W1 and W2 and B1 is a linearly independent set generating the W1 intersection W2. So this B1 can be extended to form basis of W1 and W2 by using extension theorem. So we consider the set B2 is consisting of element U1, U2, dot 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 UK, B1, B2, dot 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 Pn be basis of W1 and B3 equal to U1, U2, dot 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 UK, W1, W2, dot 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 Wm be basis of W2. Then dimension of W1 will be the number of element in P2. That here the number of element is there are K U's and the N P's. So dimension of W1 will be K plus M and dimension of W2 will be there are K U's and M W's. So dimension of W2 will be K plus M and dimension of W1 intersection W2 will be there are K U's. So dimension of W1 intersection W2 will be K. So right hand side of this equation time W1 plus time W2 minus time W1 intersection W2 will be this plus this minus K. So this is equal to K plus N plus M. Next we shall show that B equal to the vector U1 U2 dot 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 UK B1 B2 dot 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 Pn W1 W2 dot 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 Wm is the basis of W1 plus W2. That is K U's, N P's and M W's. These are the list of elements in the basis of W1 plus W2. We shall show that this vector B is a basis for W1 plus W2. For that we have to show B is linearly independent, then linear span of B is equal to W1 plus W2. First we are going to show B is linearly independent. Let alpha 1, alpha 2, dot 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 alpha k, beta 1, beta 2, dot 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 beta n, gamma 1, gamma 2, dot 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 gamma m be scalars such that linear combination of these scalars with the vectors of B is equal to 0. We put this equation 1, then rearrange the term in the next step as gamma 1 w1 plus dot 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 gamma m wm is equal to minus of alpha 1 u1 plus minus of alpha 2 u2 plus dot 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 minus alpha k uk plus beta minus beta 1 b1 minus beta 2 b2 plus dot 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 minus beta n vn belongs to w1 as this u1 u2 dot 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 uk b1 b2 dot 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 bk vn is represented by set b2 and linear span of B2 equal to W1. So the right hand side of this expression belongs to W1 and consequently left hand side belongs to W1. As B2 is this vector U1, U2 dot 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 UK, B1, B2 dot 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 Bn. Their linear combination is given as gamma 1 W1 plus dot 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 gamma m Wm. Again, linear combination of this vector with 0 coefficient for u's, that is 0 u1 plus 0 u2 plus dot 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 0 uk plus gamma 1 w1 plus gamma 2 w2 plus dot 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 gamma m wm, which is the element gamma 1 w1 plus gamma 2 w2 plus dot 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 gamma m wm belongs to w2. As this element belongs to W1, again these elements belong to W2, therefore this element belongs to their intersection. That is gamma 1 W1 plus dot 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 gamma m Wm belongs to W1 intersection W2. And B1 equal to U1 U2 dot 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 UK is the basis of W1 intersection W2. Since B1 is the basis of W1 intersection W2, so there exists a scalar delta 1, delta 2 up to delta k such that gamma 1 W1 plus dot 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 gamma m Wm can be expressed in terms of linear combinations of the element of B1, that is delta 1 U1 plus delta 2 U2 plus dot 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 delta k UK. In the next step, we bring this term to left hand side. It will then rearranging the term. It will the right hand side will be 0. The left hand side is the linear combination of the vectors of B3. As B3 is linearly independent, B3 is the basis for W2. B3 is linearly independent, so these scalars are 0. The scalars here are 0. Again from the equation 1, this gammas are 0. So equation 1 left with alpha 1 u1 plus alpha 2 u2 plus alpha k uk beta 1 p1 plus beta 2 p2 plus dot 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 beta and pn equal to 0. And here u1 u2 dot 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 up to uk b1 b2 up to bn are the vectors of B2, and B2 is a basis of W1. That means B2 is linearly independent and linear span of B2 is W1. So this scalar has this U1, U2 up to UK, B1, B2 up to Bn is linearly independent. So this scalar alpha 1 is 0, alpha 2 is 0, up to alpha k is 0, beta 1 is 0, beta 2 is 0, up to beta m is 0. Therefore, B is linearly independent. Next, linear span of B is equal to sum of the subspace W1 plus W2. As linear span is a subspace of the vector space W1 plus W2, so linear span is a subset of W1 plus W2. Next, we are going to show that W1 plus W2 is a subspace of linear span of B, for which we consider x equal to x1 plus x2 be any element of W1 plus W2, where x1 belongs to W1 and x2 belongs to W2. Since B2 and B3 are bases of W1 and W2, so there exists scalars alpha 1, alpha 2 up to alpha k, beta 1, beta 2 up to beta n, gamma 1, gamma 2 up to gamma k, delta 1, delta 2 up to delta m. Such that x1 is a linear combination of, as x1 belongs to W1 and B2 is a basis of B2 is a basis of W1. So x1 can be represented as linear combination of this element with the help of the set of scalar. So I can write this x1 as linear combination of alpha 1 u1 plus dot 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 alpha k uk plus beta 1 p1 plus dot 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 beta and pn. Again, x2 belongs to w2 and w2 is spanned by b3. B3 the set consists of u1 u2 up to uk w1 w2 up to wk. So x2 can be expressed as linear combination of the set of vector of b3, that is this B3, that is just W1, W2 up to WM and U1, U2 up to UK. So x2 is equal to this one. Therefore, x equal to x1 plus x2. Here we are getting, after rearranging the term, writing U1 with U1, that is alpha 1 plus gamma 1 U1 plus dot 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 alpha k plus gamma k UK plus beta 1 B1 plus dot 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 beta n Pn plus delta 1 W1 plus dot 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 delta m Wm belongs to linear span of B. Therefore, every element in W1 plus W2 belongs to the linear span of B. That means W1 plus W2 is a subset of linear span of B. Therefore, linear span of B is equal to W1 plus W2. Hence, B is a basis of W1 plus W2. Consequently, dim of W1 plus W2 is equal to dim of W1 plus dim of W2 minus dim of W1 intersection W2, because from this we can Find out time of W1 plus W2 will be K U's, N B's, and M W's. That is K plus N plus M, and this is equal to this, the right hand side. Therefore, time of W1 plus W2 is equal to time of W1 plus time of W2 minus time of W1 intersection W2. Next is example. Let B be a three-dimensional vector space with A and B, its subspaces of dimension 2 and 3 respectively. If A intersection B is 0, then check out which of the following is correct. Answer. Since A intersection B is equal to 0, so dimension of A intersection B is equal to 0. Now dimension of A plus B can be written as dimension of A plus dimension of B minus dimension of A intersection B. Here in the question it is given dimension of A is 2 and dimension of B is 1 and dimension of A intersection B is equal to 0. That means putting the value in the right hand side of this equation, we will get dimension of A plus B equal to 3, which is equal to dimension of B. There is a theorem. A subspace of a finite dimensional vector space is finite dimensional and dimension of the subspace is less than equal to dimension of the vector space, and dimension of the subspace is equal to dimension of the vector space if and only if the subspace is and the vector space corresponding subspace and the vector space is same. So by that theorem, I will get B is equal to A plus B. This theorem is given in the practice session. You should solve that theorem. Your answer is your B. Okay, as B is equal to A plus B, so B is my answer. Next, if the vector 1, 1, 1 is linearly independent vector in R3, are extended to form a basis of R3. The vector 1, 1, 1 is a non-zero vector and is therefore linearly independent. Let us denote the vector by S. Then linear span of S is given by alpha 1, 1, 1, where alpha belongs to R. Now, the element 1, 0, 0 belongs to R3 as this is the element in the standard basis of R3, but 1, 0, 0 vector does not belong to linear span of S. Therefore, the set S1 consisting of the vector 1, 1, 1 and 1, 0, 0 is linearly independent. Now, linear span of S1 is given by alpha into the vector 1, 1, 1 plus beta with the vector 1, 0, 0, where alpha beta belongs to the field. Then linear span is given by using scalar multiplications and the vector addition. I will get linear span of S1 equal to alpha plus beta, comma alpha, comma alpha. That is, this is the linear span is consisting of the vector alpha plus beta with alpha, alpha, where alpha beta belongs to R. Again, the element 0, 1, 0 belongs to R3 as this is an element of standard basis for R3, but it does not belong to linear span of S1. So by the theorem of linearly independent and dependent set, we can get S2 equal to the vectors 1, 1, 1, 1, 0, 0, 0, 1, 0 is linearly independent subset of R3. And dimension of R3 is equal to 3 if S is a linearly independent subset of a vector space V and dimension of vector space is same as the number of elements it has, then that set will be the basis of the vector space. This is from the theorem in the linearly independent and dependent portion. You should check it out. So here we can conclude S2 is a linearly independent subset of R3 and dimension of R3 is 3. So S2 is a basis of R3. Here, if I take another element that is 0, 0, 1, which is the element of the standard basis of R3, then I will get a different set of vector in the basis. So here I was given a non-zero vector and asked it to extend non-zero vector are linearly independent and asked it to form a basis of R3. This much is sufficient. Next, let A equal to A, B, C, 0. A is the collection of all element of the form A, comma B, comma C, comma 0, where ABC belongs to her, and B is the collection of all element of the form 0, comma D, comma E, comma F, where D, E, F belongs to her. B two subspaces of R for R. Find the dimension of the subspace A plus B. We know the standard basis of R4 is S equal to 1, 0, 0, 0. Second vector is 0, 1, 0, 0, 0. And third vector is 0, 0, 1, 0. And fourth vector is 0, 0, 0, 1. Let S1 be the subset of S consisting of vectors 1, 0, 0 and 0, 1, 0, 0, 0, 0, 1, 0. Be the subset of S that span A. S1 being the subset of linearly independent set is linearly independent for any element x, y, z, 0 belongs to A can be expressed as the linear combinations of the element of S1 as this x, y, z equal to 0 equal to x into the vector first vector of S1 plus y into second vector of S1 plus z into third vector of S1. That means any vector in A can be expressed as linear combinations of the element of S1. So linear span of S1 is equal to A. Hence S1 is the basis of A. Therefore dimension of A equal to 3. The number of elements in the basis of the vector space A will be 1, 2, 3. So dimension is 3. Again, I consider S to be the collection of vector 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Then S2 is a subset of S that is span B. S2 is a subset of linearly independent set is linearly independent for any element in B2 for any element in B 0 for any element 0 p q r in B can be expressed in terms of the vectors of S to S. 0 p q r is equal to p 0 1 0 0 plus q 0 0 1 0 plus r 0 0 1 r, which belongs to linear span of the element of S2. This implies linear span of S2 is equal to B. That means S2 is a basis of B. Therefore, dimension of B equal to 3. Again, you can check out what will be the element in A intersection B. In A intersection B, we will have collection of all these elements in A and B, where first vector is 0 in A and last vector is 0 in B. That is of this form. The element of A intersection B will be of this form 0 BC 0, where BC belongs to R. S equal to S1 intersection has 2, where S1 is my this vector and S2 is this vector. Their intersection will be this vector and this vector, this vector and this vector. So this vector will span my A intersection B. That means basis of A intersection B will consist of these two elements. So dimension of A intersection B is 2. We know that time of A plus B is equal to time of A plus time of B minus time of A intersection B. So put the value of time of A, time of B and time of A intersection B. I will get time of A plus B is equal to 3 plus 3 minus 2. That is time of A intersection B is 2. So put here 2. Time of A is 3 and time of B is 3. Put the value of time of A, time of B and time of A intersection B. I will get time of A plus B equal to 4. These are questions for your practice. You can solve this one. In case of any problem, any doubt, do not wait for the end of the unit for practice session. You can come to the department and clear your doubt at any time, any day. With that, I would like to conclude. Remaining will be in the next class. Thank you.